This is a question on atmospheric pressure and also liquid pressure. We are told that in this setup, some of the air is pumped out from T, and when we do so, the liquids, which is oil and water, will rise up the U-tube as seen in figure 11.2. And in part A, we are to explain why is this the case. Now, the reason for this is because as we pump out air from T, the inside air pressure, which started off at the same atmospheric pressure because it's air inside, this interior air pressure will decrease. The external atmospheric pressure is now bigger than the inside air pressure, and this presses down on the liquid, therefore pushing the liquid up the U-tube. In part B, you are told that this water rises 50 cm up in the U-tube, and you are to calculate the air pressure for the air that remains in the U-tube. Even though some of the air is pumped up, there is still some air remaining inside the U-tube, and we have to find the air pressure of it, which will be a value that is smaller than atmospheric pressure. So part B is a standard pressure question. We must remember that pressure along a horizontal line when everything is in equilibrium will have the same pressure throughout. So over here you can see that I've drawn a horizontal line and I've marked out two dots, one green dot and one yellow dot. These two positions will have the same pressure. On the green dot, what is causing the pressure? It is atmospheric pressure pushing down at this position. For the yellow dot, what is causing the pressure at the yellow dot? It will be the interior pressure of everything, meaning the rho GH water pressure that is pushing down at this point, and also the air pressure that is pressing down on this point too. So with this setup, the 2 points along the same horizontal line have the same pressure. I've color coded the equation based on the diagrams, and the inside pressure is made out of the whole column of liquid pressing down, and also the air pressure that is pressing down on the water, which is pressing down at these points. Rearranging the equation, we will get the pressure of the air that remains in the U-tube to be 95,000 Pascal. In this part, you are to find the density of the oil, and you're told that the oil rises by 60 cm. We will use the same technique as in part B to solve this question. So again, we recall that along a horizontal line, all pressures along this horizontal line must be the same when the liquid is in equilibrium. So again, there are 2 points marked out. On the green dot, atmospheric pressure is pressing down on it. On the green dot, on the yellow dot, uh, the air pressure in the U-tube and the oil pressure in the U-tube is pressing down on it. So these two pressures are the same. Rearranging the equation, we can find out that the pressure of the oil is 5,000 Pascal. Now, pressure of the oil is a liquid, therefore I will just use rho GH for liquid pressure and equate it to 5,000 Pascal. And we are given the value of we are given the value of the heights, which is 60 cm. Remember to convert it to SI units, which is 0.60 meters. The gravitational acceleration value is given as 10, and we can then work out that the density of the oil is 830 kilometers per meter, kilograms per meter cube. Now in part D, you're asked if we bring this whole setup to the top of a mountain, what will be the effects? Now, when we bring the whole setup up to the top of the mountain, the difference is in atmospheric pressure. As we go higher up, air gets thinner, and atmospheric pressure gets lower. So this atmospheric pressure, if it becomes smaller, the difference in pressure between the green and the yellow arrow will be lesser. There will still be a difference in pressure, therefore the liquid will still rise up to U tube when air is pumped out from T. However, the heights that the liquid will rise to will become smaller because of a smaller pressure difference between the external atmospheric pressure and the internal pressure.